we are going to understand the topics of nerve muscle physiology. In this 1.5 hour, we will try to cover all the concepts according to the important topics regarding the first professional exams, irrespective of the universities, right? What are the important topics? These are resting membrane potential, action potential, neuromuscular junction, mechanism of muscle contraction, and properties of skeletal muscle. Most important topics are action potential and neuromuscular junction. These topics are the hotspot topic here. So accordingly, we are going to understand concepts with notes, which are very much essential for your exam purposes, right? So let's go. So first of all, resting membrane potential. So what is resting membrane potential? It is the difference between electrical potential existing on the outside and inside of a cell. So let's go. It is the difference between electrical potential existing on the outside and inside of cell. At rest, because there is no ionic exchange, and the ions are some ions are inside the cell and some are outside of the cell, right? So it is the electrical potential outside and inside of cell, right? So RMP in different cells are different values of resting membrane potential there. In neurons, RMP is minus 70 millivolt, right? In skeletal muscle, RMP is minus 90 millivolt. In intestinal smooth muscle, RMP is minus 50 millivolt. So why these values are different to the different cells? Let's understand that why the values are different and how we calculate that RMP, that resting membrane potential of a cell in that resting phase. How we calculate? So firstly, we have to understand that certain ions have certain concentration in ECF and in ICF. ECF means extracellular fluid and ICF intracellular fluid. So here is a cell and here is the blood vessel. In between them, it is the interstitial space. So it is the intracellular compartment and rest are extracellular compartment. So obviously this compartment contains ICF and these two are containing ECF, right? So look at the values first. Sodium ion is higher in the ECF. So we're writing that sodium is higher in concentration in the ECF, right? And it is very less in ICF, right? Whereas potassium is more in amount in ICF than in the ECF, right? Also chloride is more in ECF than in ICF, right? So these are the ionic configuration inside and outside of the cell, right? Now there is another component inside the cell, that is protein. Protein is anionic in nature, but it cannot cross the cell membrane because it is too large. It is anionic, too large to cross cell membrane, right? So protein cannot cross the cell membrane. Okay. Potassium will move inside to outside along its concentration gradient, right? And sodium will enter inside the cell. But here is one problem. Sodium is nearly impermeable to the cell membrane, so very less amount of sodium is entering into the cell, right? So this amount is very less, right? This amount is very less. So intracellular negativity is persisting. Why? Because protein is anionic, potassium is going outside of the cell, very less amount of sodium is entering into the cell, and chloride cannot go against the concentration gradient. So all over a negativity persists inside the cell. So intracellular negativity persists, right? So intracellular negativity persists. Though intercellular negativity persists, but we have to calculate that RMP value. Here we proceed some conceptually. So here is the potassium which is going outside of the cell, right? So after going outside of the cell, the concentration level is equal. Or if potassium is in a meantime, let's say potassium is more outside of the cell, then it comes intracellular, right? So there is a diffusion between intracellular and extracellular potassium. So for this diffusion, we calculate diffusion potential of a ion. For this diffusion potential, we use Nernst equation. So Nernst equation is E, that ion, equal to RT by Fz log or natural log that ion outside of the cell by ion inside of the cell. For potassium ion, EK plus equal to RT by Fz. What is R? R is the gas constant. What is T? T is the absolute temperature. What is F? F is Faraday. And what is Z? Z is the valency of the ion. So here we calculate that value RT by Fz of natural log, and for potassium that value is 61.5. We convert natural log into the log, and potassium outside by potassium inside. So that's equal to 61.55 log. Potassium outside is 4. So potassium is less in the ECF, that's 4, by potassium inside is much higher, that is 155, that unit in millimole per liter. Okay, so by this calculation, that's equal to minus 90 millivolt approx, right? Similarly, for Na plus, for sodium ion, ENA equal to plus 65 millivolt, and for chloride ion, E chloride equal to minus 70 millivolt. Here we got all the diffusion potential of all ions, right? From here we can predict the resultant RMP value of the cell. Here we mainly talking about the nerve cells or the neurons. So potassium is minus 90 millivolt, sodium is plus 65 millivolt, and for calcium, for chloride, it is minus 70 millivolt. Now we previously talking about the permeability of the sodium ion. Sodium ion is very less permeable when it comes inside of the cell than that of potassium ion that is going outside of the cell. So potassium ion is 10 to 25 times more permeable than sodium ion, and actually that resultant RMP value very much dependent on the permeability and the conductance of that ions, right? Very much dependent on the permeability and conductance of ion. So we can predict the RMP value that it will near the minus 90 millivolt. It will definitely nearest value of minus 90 millivolt. For that we have equation that is known as Goldman-Hodgkin-Cass equation. Where RMP equal to RT by F natural log of P of potassium ion. Here P stands for permeability, right? Here P stands for permeability, right? Potassium ion outside of the cell plus P of sodium, permeability of sodium, into sodium ion outside of the cell plus permeability of the chloride ion and chloride ion outside of the cell by permeability of the potassium ion into potassium ion inside of the cell, and that also for the sodium ion and also for the chloride ion. Here there is no such chloride ion, and chloride ion cannot permeable to the cell membrane. That's why this permeability cancels out, and it is very much dependent on the sodium and the potassium ion. And for the nerve cell, that RMP value equals to minus 70 millivolt. Hence, from that Goldman equation, we can measure RMP for any kind of cell, right? So it is the important equation, Goldman equation, as it is very much dependent on the potassium ion and the sodium ion. It is also very much dependent on sodium, potassium, ATPase activity, right? Or we can say sodium potassium ATPase pump, right? So it is very much dependent on that pump, where 3 sodium ions are going outside of the cell and the 2 potassium ions are incoming in the cell, and by the expenditure of the ATP, right? So that is the whole calculation and the concept behind the resting membrane potential. So next comes the donor equilibrium. So what is the concept behind donor equilibrium? When two solutions, let's say A and B are the compartment where the solutions are kept, in A compartment we have potassium ion, chloride ion, and non-diffusible protein, let's say A negative anion, and in the B compartment there is potassium ion and chloride ion. So there is a membrane in between them. Let's say this is a membrane or you can say semi-selective membrane. Some are permeable through this membrane, some ions are permeable through this membrane, and some are not, right? So here potassium and chloride are permeable through this membrane, but anion A is not permeable through the membrane. So what is the concept? Basically, concept is the concentration of compartment A is greater than the concentration of compartment B, right? We can write concentration of potassium plus concentration of chloride plus concentration of A greater than concentration of potassium plus concentration of chloride, which are in B, and that potassium and chloride in A, right? Why? Because here we cannot as there is a concentration, higher concentration in A, in compartment A than in compartment B. Due to osmosis factor, solvent are coming from B to A due to concentration against the concentration gradient, you can say, in osmosis. And there are two scientists, Gibbs and Donan. They put it in a mathematical equation. Scientists are Gibbs and Donan. This says that potassium in compartment A by potassium in compartment B, which is equal to chloride in compartment B by chloride and in compartment A. This is known as the Donan equilibrium, or the Gibbs-Donan equation on the basis of diffusible ions. So the basis of the equation is osmosis of solvent along with diffusible ions. So that's all for the racing membrane potential, all the concepts. And now we are moving to the very important topic, that is action potential. Action potential, it is a very important topic. So what is the action potential? Action potential, it is a sequential charge in the membrane potential due to opening and the closing of the different types of ion channels, right? So, and there is a propagation along the excitable tissues like neurons, neuronal axons, right? And that propagation is called propagation. Along with that sequential change is known as action potential. Then the definition is the sequential change in membrane potential due to opening and closing of various types of ion channels and its propagation along the excitable tissue is known as action potential. Okay, so action potential, main key points are sequential change, opening and closing of various types of ion channels, and the propagation along the excitable tissue, right? Now we are going to understand different phases of the action potential in a nerve, or you can say axon, right? So here we can clearly understand different phases of action potential, right? So let's say there is a stimulus given at this point, at this very time, a stimulus is given, but that stimulus is not up to that mark, which can lead at resting membrane potential minus 70 to the threshold potential minus 55 millivolt, right? So there is a stimulus artifact. So this is the stimulus artifact. This is the stimulus artifact, and now for a short interval there is no stimulus. Again the stimulus starts from here. So the time between the first stimulus and the next stimulus, it is known as latent period. Now at the end of latent period, the membrane depolarizes. The first 7 millivolt, some 7 millivolt depolarization is entirely passive, and there is no active participation from cell membrane itself. So there is a rise in potential. When the depolarization range is around 7 to 15 millivolt, the voltage gated sodium channels open, causing entry of sodium into the cell, right? But however, the repolarization forces are greater than depolarization force. So depolarization cannot take the upper hand in this moment. But sooner or later, when the membrane potential reaches minus 55, when it reaches minus 55 millivolt, then in a moment, large number of voltage gated sodium channels opens up simultaneously, right? So there is a third stop, or the you can say explosive entry of sodium ions into the cell, causing a massive depolarization. It is a shoot up of the entry of the sodium ions, right? So sodium ion enters. Sodium ion enters, and it goes above 0 millivolt, which is known as overshoot, and the total sharp in the membrane potential is known as upstroke. So this phenomenon is known as depolarization, right? The first phase is the depolarization. First phase is the depolarization. So it ends up in the plus 55 millivolt. Sorry, plus 35 millivolt. So it ends here. In the depolarization, we see that there is massive rise in intracellular positivity due to massive sodium entry into the cell. So main feature is the sodium entry into the cell by voltage gated sodium channels. Now after overshooting, the membrane potential falls due to several reasons. Reasons are: number one, there is inactivation of sodium channels, which is time and voltage dependent. Time and voltage dependent. Secondly, entry of sodium ions into the cell in large amount reverses the electrical gradient. So further influx of sodium ions is opposed. Thirdly, efflux of potassium ion begins at the end of this stage, due to which intracellular positivity decreases. Now what happens? The membrane potential falls down, and it certainly goes into the hyperpolarized state. So it is not like that, it is like that. So it is the after depolarization, which is the repolarization state. It is the repolarization state, and this here more and more amount of potassium is going outside of the cell. So here membrane potential is below minus 70 millivolt, or the resting membrane potential, right? So this stage is known as hyperpolarization. In repolarization, in the depolarization state, where in depolarization state this is known as upstroke. In depolarization it is known as downstroke. The fall in membrane potential, it is known as downstroke, right? So there are three phases: depolarization, repolarization, and the hyperpolarization state in the action potential in a nerve or axon. Now we are moving to the very important concept of refractory period. So now we are going to understand very important concept regarding refractory period. So what is the refractory period? During the action potential, the excitable tissue shows diminished responsiveness, right, to the external stimulus. So that period where it shows that diminished responsiveness, that is known as refractory period. So we write the definition. During action potential, the excitable cell or the excitable tissue, whether it is nerve or muscle, shows diminished responsiveness. This period of diminished responsiveness is called refractory period. Here diminished responsiveness means some ion channels are inactivated, and new second action potential is not generated in this meantime. So there are two types of refractory period. Two types of refractory period. First one is absolute refractory period, and second one is relative refractory period. So one is absolute refractory period, another one is relative refractory period. So in this picture we can see that the absolute refractory period is from the stimulus is given to the 1/3 1/3 period of the depolarization or the dump stroke. So in this meantime, we cannot generate another action potential, right? Where sodium channels are inactivated and there is no entry of sodium, and second action potential is not possible in the absolute refractory period, right? So from here to here, there is no new action potential is generated, right? So ARP, absolute refractory period, from the onset of depolarization to about 1/3 of repolarization, nerve or muscle cannot be excited. However strong the stimulus may be. So in any kind of stimulus, if that muscle or nerve cannot be excited, stimulus may be, right? So this period is known as absolute refractory period. So during the early part of upstroke, the second action potential is not possible due to sodium channels are already fully open, and sodium entry at the greater rate is not possible. During the remaining time, absolute refractory period, sodium channels are inactivated, right? So no new action potential is generated in this time. From now, what is the relative refractory period? From 1/3 of the depolarization up to the end of another after hyperpolarization, right? That means from 1/3 of the depolarization to the end of hyperpolarization, there comes the relative refractory period. The excitable tissues can be excited only by a stronger than a normal stimulus. So it lasts for 10 to 15 milliseconds. So here action potential is generated if stimulus is stronger than normal. So it is the new action potential is generated if the stimulus is stronger. So relative refractory period from the 1/3 of repolarization up to the end of after hyperpolarization, the excitable tissue can be excited only by a stronger than normal stimulus. Right. So it is that diminished responsiveness, obviously, and there is two types of refractory period, absolute and relative. In absolute, nerve or muscle cannot be excited, however the strong stimulus may be, and in the refractory one, that excitable tissue can be excited only by a stronger stimulus, right? Now comes the final concept of propagation of action potential. Final concepts means in the concept of action potential, it is the final one, propagation of action potential. In propagation of action potential, we describe the propagation of action potential in both types of nerves. Firstly, unmyelinated nerve fibers, and secondly, the myelinated nerve fibers. So we classify that into two parts. So first one is unmyelinated nerve fibers, propagation of action potential in unmyelinated nerve fibers. Secondly, propagation of action potential in myelinated nerve fibers. Firstly, we see how it looks like, how an unmyelinated nerve fiber looks like. So that is the, let's say, neuron and its terminal branches. So that is unmyelinated, without myelin sheet, right? So that is the neuron, that is the axonal part, and that is the cell body, and these are the axonal terminals. We are interested in the axon, right? So there is no myelin sheath, right? So this is the axon. So it is the it is outside the axon, it is the inside the axonema, right? Let's say here action potential is generated. Here is the action potential is generated. So it is propagating nearby by replacing those ions and and again, and these charges are propagating in the forward direction. Now the scenario is like this. So now the charge is propagating like this in the linear way, in the continuous manner. Let's say let's talk it in the continuous manner. But in the myelinated nerve fibers, there is a special mechanism for propagation of action potential. There are myelin sheaths. So these are the myelin sheaths, and these are the nodes of Ranvier, right? So the action potential where it is generated, let's say action potential is generated here. So these all are negative. So this charge is propagating in a jumping manner. So let's say here also it propagates in the jumping manner. So in next stage, it also jumps from one node of Ranvier to another node of Ranvier. So it is known as saltatory conduction, right? So it is known as saltatory conduction. This is jumping from one node of Ranvier to another node of Ranvier in a myelinated nerve fibers is known as the saltatory conduction. So it is known as saltatory conduction. Okay. So here we cover all the important topics of action potential. So firstly, from the definition and the phases of action potential in a nerve, which is very, very important. It comes as a short note, and there is an important concept regarding refractory period, absolute and relative refractory period at there. And finally, there is propagation of action potential with a special type of propagation which is known as saltatory conduction. Now comes the next very, very important topic, is the neuromuscular junction. So neuromuscular junction, it is basically a anatomical junction between a motor neuron and a muscle cell right? So it is an anatomical junction between a motor neuron and a muscle cell, where an action potential is transmitted along the motor neuron is converted into an action potential in the muscle cell. So basically this junction conveys the action potential from the neuron to the muscle cell, or we can say the motor end plate, right? So where an action potential is transmitted along the motor neuron, converting into action potential into the muscle cell. So it's like a synapse. In synapse, this is in synapse it is neuron junction, and in the neuromuscular junction it is a neuron to muscle junction, right? So it is an anatomical junction between a motor neuron and a muscle, and the action potential is transmitted from motor neuron to the muscle cell, right? So in this picture we can depict different parts of this junction. Firstly, there is action potential. This arrow depicts that action potential is running down to the motor neuron, axon of the motor neuron, and this is a axonal terminal. It is a axonal terminal, right? And here it is the motor end plate, where the axonal terminal is embedded. In between the neuron and the motor end plate there is a cleft. As you know that in synapse there is a synaptic cleft between presynaptic neuron and the postsynaptic neuron. In case of neuromuscular junction, that is not the synaptic cleft, it is a neuromuscular cleft. Rather, it is a neuromuscular cleft. So that is the neuromuscular cleft, right? This you can recognize that these are the synaptic vesicles with full of that neurotransmitter. Example is acetylcholine. Acetylcholine, right? So in the synaptic cleft, this all are the acetylcholine. This structure is acetylcholine esterase. Acetylcholine esterase, and this yellowish box is the acetylcholine gated sodium channels. So the important parts of the neuromuscular junction are: first one is axonal terminal, second one is motor end plate, third one is neuromuscular lift, right? Neuromuscular cleft. So these are the parts of the neuromuscular junction, and there are synaptic vesicles in the axonal terminal. Yes, voltage gated channels are also the part of the neuromuscular junction, right? So SH, or the neurotransmitter gated sodium channels. So these are the parts of the neuromuscular junction. Let's talk about different terminologies like motor end plate and the motor unit. So what is motor end plate basically? It is a where the terminal buttons of the single axon terminal become attached to a thickened portion of the muscle membrane. That area or that membrane is known as the motor end plate. So terminal buttons of a single axon terminal become attached to a thickened portion of the muscle membrane. Which is known as motor end plate. So here are the terminal buttons of the axonal terminal and attached with thickened portion of muscular membrane, that is known as motor end plate. Now, what is motor unit? Motor unit, it is a combination or we say consists of a single motor neuron and all the muscle fibers which that neuron innervates, right? So the definition is a motor unit consists of a single motor neuron and all the muscle fibers it innervates, right, like this one. Let's say this is motor unit 1 and it is motor unit 2. Motor unit 1 supplies this muscle fiber and this muscle fiber, right? So this is these two muscle fibers are the motor unit of that particular motor neuron. In a similar way, motor unit 2, there is one fiber, second and the third, three fibers are there with the motor unit. So three muscular fibers are the motor unit of that single motor neuron of the motor unit 2, right? So mainly its function is the primary role of the motor unit is facilitate the muscle contraction. So primary role is muscle contraction, right? So it is the motor unit where a single motor neuron supplies different types of different muscle fibers, right? To different muscle fibers. Now come the most important one, that is the mechanism of neuromuscular transmission. Mechanism of neuromuscular transmission, it's a very important topic in all exams and it is a very important concept to understand. We understand this topic in a flowchart manner that we can understand it very thoroughly, right? So firstly, what happens that action potential travels along axon towards the axon terminal, right? So first step, action potential travels along axon towards the axon terminal. Okay, so this happens in motor nerve fiber. Okay, happens in motor nerve fiber. Then opening of voltage gated calcium channels. Why? Because action potential is coming down to the axonal terminal and the intracellular positivity increases. Intracellular positivity increases, due to which opening due to which calcium channels, that voltage gated calcium channels are opened due to that intracellular positivity or the depolarization in the axonal terminal. Opening of voltage gated calcium channels in the axon terminal. Okay, then calcium enters into the axon terminal. So the purpose of the calcium here in the axonal terminal is to exocytosis those synaptic vesicles which are filled with neurotransmitter like acetylcholine. So opening of vesicles and release of acetylcholine. Opening of vesicle happens here and acetylcholine release. Right, means this is the exocytosis phase. So calcium helps in exocytosis of that vesicles. Or the exocytosis of the acetylcholine in synaptic or the neuromuscular cleft. Okay, so this all happens in the axon terminal. Then what happened? Then acetylcholine binds with N1 nicotinic receptor in the postsynaptic muscle membrane, right, in the motor end plate. So those acetylcholine molecules binds with N1 nicotinic receptors in the post synaptic muscle membrane in motor end plate, Okay, then opening of ion channels incorporated with acetylcholine receptors. So here is opening of sodium channels, right? Sodium channels, those ligand gated sodium channels. Opening of small ion channels incorporated in acetylcholine receptors. So basically there are two types of receptors are here, two types of channels are here. One is ligand gated and another one is voltage gated. So firstly what happens that ligand gated sodium channels are activated due to the incorporation of the acetylcholine molecules. Then when the positivity increases as a bit by bit, then the voltage gated sodium channels also opens and allows enter of the sodium ions into the motor end plate, right? So that is entry of sodium ion entry into the muscle cell from extracellular fluid. So if sodium enters, what happens? Depolarization happens. So depolarization leading to motor end plate potential. This all happens in the postsynaptic muscle membrane or in the motor end plate. This all steps, including depolarization, these all steps happen in the postsynaptic muscle membrane. Okay, then the motor end plate potential is generated and current sink produce depolarization in the neighboring muscle membrane or in the in the sarcolemma, right? So motor end plate potential is generated and a current sink is produced. Current sink produces depolarization in neighboring muscle membrane. Okay. Again, when it's cross, like action potential, when it crosses that motor end plate potential crosses threshold, action potential in the muscle forms. Action potential forms inside the muscle cell sarcolemma. Muscle cell sarcolemma, and that action potential runs along the sarcolemma. Action potential runs along sarcolemma. Later we understand that very important concept of excitation contraction coupling. So this whole part is the excitation part, right? Contraction is in the molecular level of that sarcolemma. Okay, so that is the excitation part, and it is a very important part of the flowchart of neuromuscular transmission also. So these last steps are happening in muscle fibers, right? So we can clearly see in image that here the action potential comes, right? Action potential comes, intracellular positivity increases, entry of calcium channels through the voltage gated calcium channels, right? Calcium enters, and there are some vesicles over here. Calcium helps them to exocytosis the neurotransmitter into the synaptic cleft. These are the acetylcholines, right? Acetylcholines are moving out in the synaptic cleft, and there are some receptors also that are some are ligand gated sodium channels, and some are the voltage gated sodium channels. So with them acetylcholines bind with them, and there is enter of the sodium ions from ECF, and also there are voltage gated sodium channels through which after sometimes sodium enters. So there is a summation of the potential, and which comes into the depolarization, right? And the production of motor end plate potential, right? Then it goes to the neighboring muscle fibers and forms the action potential in that muscle fibers and run along the sarcolemma. Okay, that is the main concept of the neuromuscular transmission and the first part of the excitation contraction coupling, which we will understand later. So this is a very important concept of neuromuscular transmission. Okay, so it comes as a short note in your exams, and you need to understand this topic very well also. Next comes the difference between synapse and neuromuscular junction. Both resembles very similar, but there are some contrast among them. So let's write down one by one. Firstly, in features, we talk about that connections between which part among them, right? So connections in synapse, it is between neuron and a neuron. Neuron to neuron, right? Whereas in neuromuscular junction, it is between neuron to skeletal muscle cell. Okay, then excitatory or inhibitory type of transmission it is. So it is where synapse provides both excitatory and inhibitory responses, whereas in neuromuscular junction it is always excitatory. So the type of the postsynaptic potential. Okay, type of postsynaptic potential. In synapse, in case of synapse, it will both excitatory and inhibitory. So it is known as excitatory postsynaptic potential, EPSP, excitatory postsynaptic potential, and IPSP, inhibitory postsynaptic potential. Whereas in neuromuscular junction, it is always excitatory. It is always excitatory, means the potential is always excitatory, means it is always EPSP. Okay, next the structures of the next the postsynaptic membrane. Structure of postsynaptic membrane. In synapse, synaptic knob is smooth and rounded. Whereas in neuromuscular junction, the end plate has brushed appearance. Microvilli end plate has brushed appearance. Microvilli is flattened up to muscle fibers. And you all know that in neuron synapse, we call that cleft. The between presynaptic neuron and postsynaptic neuron is known as synaptic cleft. But in the neuromuscular junction, between presynaptic neuron and the postsynaptic muscular membrane, it is known as neuromuscular cleft. So release of vesicles, it is in the synaptic cleft and it is in the neuromuscular cleft, right? So it was the difference between synapse and neuromuscular junction. Now let's move to the pathophysiology of neuromuscular junction. So in this pathophysiology, there are two important diseases we are talking about. The two important diseases are firstly myasthenia gravis and second one is Lambert-Eaton syndrome. So first one is myasthenia gravis. Secondly, Lambert-Eaton syndrome. Okay, let's understand by a drawing. Let's say here is the axonal terminal of a neuron and there are some synaptic vesicles which are loaded with acetylcholine. Okay, so these are the synaptic vesicles and here is the acetylcholine inside these vesicles. So there are two types of protein, V snare and T snare. When V snare and T snare are merged with it, and synaptobrevin is with the vesicles. So synaptobrevin, this is synaptobrevin, and there is two snare proteins, V snare and T snare. V snare attached with vesicles here. V snare, it is a vesicle snare protein, and T snare is attached to the terminal. So when these proteins are merged, then what happen? Then the this axonal terminal is open up, and vesicles are merged with it, right? Vesicles are merged with it, and the acetylcholine release in the synaptic or the neuromuscular cleft. So there is voltage gated calcium channels in the axonal terminal, due to which exocytosis of the vesicles happens, and calcium enters through these channels, due to which calcium stimulates that vesicle to being exocytosis in the neuromuscular cleft. So we have to understand now the pathophysiology of the myasthenia gravis and the Lambert-Eaton syndrome, right? And there, we all know there is a motor end plate. There is a motor end plate over here. So let's say this is the motor end plate. Over here, these are acetylcholine gated sodium channels, or the ligand gated, which is acetylcholine gated sodium channels, where this acetylcholine gets binded, right? Acetylcholines get bind to these receptors and open the receptor, due to which sodium enters into the postsynaptic muscle membrane or the motor end plate. Then the depolarization happens. Then the MEPP, that is motor end plate potential, is generated due to depolarization, right? So what happened in myasthenia gravis? In myasthenia gravis, autoimmunity plays a very important role. Autoimmunity plays a very important role, right? So myasthenia gravis is a type 2 hypersensitivity reaction. Hence, here autoantibodies are generated against those ligand-gated sodium channel receptors, right? So antibody is generated. Let's say these are all antibodies. These are the autoantibodies against those channel receptors, and actually they destroy those channels by which sodium enters into the motor end plate, right? So in this myasthenia gravis, autoimmune antibodies are produced against those receptors, and what happened that now acetylcholine cannot bind with those receptors because these receptors are destroyed, and no further sodium ion is entered into the motor end plate, right? That's why it leads to less muscle contraction, and the muscle weakness, and it continues with the regular activities, right? So here we write the whole pathophysiology in a flowchart manner. So main thing is the autoimmune response. Autoimmune response. There is development of autoimmune antibodies against acetylcholine receptor in ligand gated sodium channels. So then what happened? Those antibodies attacks acetylcholine receptor at ligand gated sodium channel in motor end plate, which acts against the nicotinic acetylcholine receptor. No further sodium ions enter into the motor end plate. No further sodium ions entered into the motor end plate, right, due to closure of the ligand gated sodium channels, because in the ligand gated sodium channels there are acetylcholine receptors. Those acetylcholine receptors are attacked by autoimmune antibodies, due to which ligand gated sodium channels are closed and no further sodium ions enter into the motor end plate. Very few amount, yes, there are very few amount of ligand gated channels, ligand gated sodium channels, which are not attacked by those antibodies, and those are carry sodium into the motor end plate, but those are attacked by those antibodies. They cannot further conduct the transmission of the transmission of the sodium ion into the motor end plate. They can't. So due to closure of ligand gated sodium channels, so there is decrease in or no motor end plate potential, right? There is decrease or no motor end plate potential generation, which lead to less or no muscle contraction, which further leads to voluntary muscle weakness. Okay, which further lead to voluntary muscle weakness that escalates with the continuing activity. Right? So this is the main pathogenesis of the myasthenia gravis. Now comes the pathogenesis of Lambert-Eaton syndrome. So what is the main pathogenesis over here? There are mutation in the protein which helps to make the voltage gated calcium channels, right? So there are mutation in voltage gated calcium channels. So in this voltage gated calcium channels, get mutated. So there is obviously inactivation of the voltage gated calcium channels, and calcium do not enter into the axonal terminal. So what happened, as calcium is helping in that synaptic vesicles for exocytosis, and acetylcholines move out into the synaptic vesicles. Now in absence of calcium, what happened, that synaptic vesicles cannot exocytosize, right, in outside the axonal terminal into the synaptic cleft. So there is no question about activation of those ligand gated sodium channels, and there is no further entry of sodium ions into the motor end plate. So there is no contraction, no muscle contraction. There is no motor end plate potential generation, and due to which no muscle contraction, and in this disease. So main pathology here is mutation of voltage gated calcium channels. So obviously there is inactivation of voltage gated calcium channels, right? So there is less or no opening of voltage gated calcium channels. Calcium can't enter, and which, so there is no exocytosis of acetylcholine outside the axonal terminal, in synaptic cleft. So no activation of ligand gated sodium channels in motor end plate, right? In motor end plate. So there is no contraction, there is no depolarization in the motor end plate. So there is less or no motor end plate potential generation, which further leads to the voluntary muscle weakness, right? Further lead to the again voluntary muscle weakness. And no muscle contraction, right? So this is the main pathogenesis of myasthenia gravis and Lambert-Eaton syndrome side by side and with a diagram. This is a very important question for your exam purpose. And now let's move to the some difference between myasthenia gravis and Lambert-Eaton syndrome, right? Now we will discuss the differences between myasthenia gravis and Lambert-Eaton syndrome. First difference is in the pathogenesis. Pathogenesis or the pathophysiology of the myasthenia gravis and Lambert-Eaton syndrome. In myasthenia gravis, we discussed earlier that it is due to the autoimmune reactions. It is a type 2 hypersensitivity reaction, which is between antibody and the antigen. Okay, so in myasthenia gravis, autoimmune antibody inhibits acetylcholine receptor. That is the main pathogenesis. Whereas in Lambert-Eaton syndrome, the main pathogenesis is the mutation of voltage gated calcium channels and its inactivation, due to which synaptic vesicle cannot release in their acetylcholine into the synaptic cleft, right? Its inactivation. Okay. Secondly, release of acetylcholine in synaptic cleft. What happened in the release of acetylcholine? We see in myasthenia gravis what happened. Autoimmune antibodies are generated against the ligand gated sodium channel, against the acetylcholine receptor of the ligand gated sodium channels. So in acetylcholine concentration in the synaptic cleft, there is no change because there is no pathology in the axonal terminal. There is pathology in the motor end plate, or the postsynaptic muscle membrane. So there is adequate amount of acetylcholine in the synaptic cleft. So there is no decrease in acetylcholine in the synaptic cleft. Then the release is normal. It is normal. Whereas in Lambert-Eaton syndrome, there is mutation of voltage gated calcium channels, due to which exocytosis cannot occur here. Hence the synaptic vesicles cannot fuse with the axonal terminal and the acetylcholine cannot release out into the synaptic cleft. So the concentration of the acetylcholine in the synaptic cleft is decreasing. So here release of acetylcholine decreases, right? Third, association with thymic enlargement. In myasthenia gravis, there is association with thymic enlargement because there is enlargement of the thymus in the myasthenia gravis. But in Lambert-Eaton syndrome, thymic enlargement is not seen. So here the thymic enlargement association is present in case of myasthenia gravis, and in Lambert-Eaton syndrome it is absent. Next, the time where the time when this problem occurs generally with the normal muscular activity or the beginning of the day and the prolonged rest. There is no such complication in the myasthenia gravis, but with the repeated activity, when the time passes, that acetylcholine level is decreasing due to the acetylcholine esterase. There is a enzyme that is called acetylcholine esterase into the synaptic cleft that inhibits breaks down the acetylcholine, right? So with the regular activity or with the day gradually passes, the activity increases and that autoimmune antibodies are production of autoimmune antibodies are increasing, and that destroys the acetylcholine receptor into the ligand gated sodium channels. So when the activity increases due to in the day, the problems also occurs. But in the Lambert-Eaton syndrome, with repeated attempts, there is increase in muscle contraction. There is no such complication occur. So we say that time let's say time of complication. Time of complication. Normal muscular activity. Let's say in the beginning of the day or in after prolonged rest. Complication can't occur. Not seen. But with increasing activity, or the time passes, autoimmune antibodies production rises greater than acetylcholine production. So that causes complication and symptoms. Complication and symptoms. Okay. But in case of Lambert-Eaton syndrome, with repeated attempts, there is no change. Increase or decrease in the complication. Okay. So it is the difference between myasthenia gravis and Lambert-Eaton syndrome, and you can see here clearly that pathogenesis of Lambert-Eaton syndrome is in the axonal terminal, and the pathogenesis of the myasthenia gravis is in the motor end plate, right? So there is a difference between obviously there is difference between pathogenesis of the myasthenia gravis and Lambert-Eaton syndrome. So it was so this was the pathogenesis and the differences between myasthenia gravis and Lambert-Eaton syndrome. Okay. Next comes the treatment of myasthenia gravis only. So as there is a mutation in Lambert-Eaton syndrome, mutation in the voltage gated calcium channels in the Lambert-Eaton syndrome, treatment is not there is no such treatment in Lambert-Eaton syndrome, but there is obviously the treatment in myasthenia gravis. Now we are going to see the treatment of myasthenia gravis. There is two important drugs in the treatment of myasthenia gravis. These are neostigmine and edrophonium, right? So there is two drugs in the treatment of myasthenia gravis. First one is neostigmine and second one is edrophonium. So how we use neostigmine? We do it in a flowchart manner. Neostigmine administration. First, we have to administer the neostigmine in the patient of myasthenia gravis. What is neostigmine? It is basically a acetylcholine esterase inhibitor. Neostigmine is a acetylcholine esterase inhibitor or blocker. That neostigmine inhibits acetylcholinesterase. So there is reduced breakdown of acetylcholine in the synaptic cleft of acetylcholine in synaptic cleft. So there is increased availability of the acetylcholine due to there is reduced breakdown. There is increase in the availability of the acetylcholine in the neuromuscular junction. Obviously, increased availability of acetylcholine in neuromuscular junction. Then more and more acetylcholine binds to nicotinic receptor. On the muscle membrane. And there, as there is antibody, autoimmune antibody against those ligand gated or the nicotinic receptor, acetylcholine gated sodium channels, so which are not attacked by those antibodies, they are more and more acetylcholine binds. So there is improvement of the muscle contraction and strength. Obviously, there is improvement of muscle contraction and strength, and there is reduction of symptoms of myasthenia gravis. So this is the main mechanism of action of neostigmine. It is the main treatment of the myasthenia gravis. Edrophonium is used in the diagnostic test of the myasthenia gravis. It is known as tensilon test or the edrophonium challenge test. So it is used in diagnosis by edrophonium challenge test or tensilon test. Okay, so how we apply that drug in the diagnosis of the myasthenia gravis? Let's see. Firstly, patients who are suspected with myasthenia gravis, assess the baseline muscle strength, and then we give a small amount of edrophonium. So firstly, that patient suspected myasthenia gravis. After assessing the baseline muscle strength, administration of small test dose of edrophonium. And then observe the adverse reaction. Observe the adverse reaction. If yes, then administer the antidote. If the adverse reaction is more than than we expect, then there is no myasthenia gravis in that patient, or there is less muscle strength is present, but there is no myasthenia gravis as such. So then we administer the antidote of edrophonium, that is atropine. Okay, if if adverse reaction is not present there, if no, then what we can do? Administer a full dose. So what is full dose and what is test dose? Test dose is about here we can write test dose is 2 mg by IV or the intravenously, and full dose is 8 mg by intravenously, right? So if there is no adverse reaction, then we administer full dose, that is 8 mg by intravenously, and we observe the improvement of muscle strength. Now we observe for improvement muscle strength, right? If yes, then it is the positive for myasthenia gravis. If no, if that is negative response, so that is unlikely myasthenia gravis. So by this test we can actually diagnose whether it is myasthenia gravis or it is not myasthenia gravis, right? So it is the hydrophonium challenge test or the tensilon test. So two drugs are important in the treatment of myasthenia gravis, that are neostigmine. We see the main mechanism of action of neostigmine, and the hydrophonium on the other side, where we see the diagnostic test, that is the hydrophonium challenge test on the tensilon test. So that is for the neuromuscular junction topic. It is a very important topic conceptually, and in the exam there is a question regularly come, and you have to understand concept very thoroughly. So there are terminologies, there are concept of transmission, neuromuscular transmission, and there is differences between synapse and neuromuscular junction. Pathophysiology includes that myasthenia gravis, Lambert-Eaton syndrome, and lastly the treatment of myasthenia gravis. Okay, let's come to a topic of mechanism of muscle contraction. So in this topic you have to have that concept of hierarchical structure of skeletal muscle, and most importantly there is a concept of excitation contraction coupling. So it is a very important topic in this chapter, and or in this subtopic in this topic. And mechanism of muscle contraction, we firstly understand the structure of skeletal muscle. So in the structure of skeletal muscle, well, we know that there is epimysium, perimysium, and endomysium, which is the covering of muscle fibers, and the myocytes also. And there is, in the molecular level, there is myofibrils, and in the molecular level there is sarcomere, where excitation contraction coupling is occurring. And here we have to know the sarcomere part and the different lines and bands of sarcomere. It is a contractile unit of the myofibril and the whole muscle itself. So muscle, it is covered by epimysium, muscle fascicle, it is covered by perimysium, and there are also capillaries and the nerve fibers which are embedding into the endomysium, which covers the muscle fiber. And there is a contractile unit, which is sarcomere present in myofibril, which contributes into the myofibril part. And now we are talking about sarcomere and parts of the sarcomere. Okay, so there are two types of filaments. One is thick filament, one is thin filament. Thick filament is called myosin and thin filament is called actin. So in the sarcomere unit there are two thick filament, in between thin filament is present. Okay, so firstly we draw two thin filaments side by side. Let's say these are two thin filament. Okay, and in between this there is thick filament. So let's say this is the thick filament. So it is the thick filament of the myosin, and this is the thin filament, that is actin. So we are discussing about structures of sarcomere. So firstly there is two Z lines. Let's say these two are Z lines here, between which sarcomere is present, and the line at the middle point of the thick filament is known as M line. The portion that is not covered by thin filament, this portion is known as H zone, and there is A band, which is an A band. This is known as A band. Sorry, it is sarcomere, not sacromere. It is sarcomere. Okay, and the length between the one end of the thick filament to the Z line is known as I band. As we are viewing in 2D, but in 3D, one thick filament is surrounded by 6 thin filament. It is a 2D structure. In 3D, one thick filament surrounded by 6 thin filaments. Okay, let's move to the next one, that is excitation contraction coupling. In excitation contraction coupling, we are seeing a section of myocyte. This is a section of myocyte. That I told you earlier that the excitation part of the excitation contraction coupling, excitation already we saw in the neuromuscular transmission, where the voltage gated sodium channels are open, ligand gated sodium channels are open. That increases the motor end plate potential, and also it stimulates the voltage gated sodium channels, which further excites and generates action potential inside the muscle fiber. We see it in the neuromuscular junction. From the action potential generated in the myocyte, we will discussing in the contraction part of the excitation contraction coupling. Firstly, these are the ligand gated sodium channels, and these are the voltage gated sodium channels. Sodium enters first through the ligand gated sodium channels, right? So depolarization occurred, motor end plate potential generation, and then it crosses the threshold potential inside the myocyte, which in turn stimulates the voltage gated sodium channels, from where also sodium is entered into the myocyte, and there is massive depolarization, due to both ligand gated sodium channels and the voltage gated sodium channels. Sodium are accumulating inside the myocyte, which causes massive depolarization and action potential generation in the muscle fiber, which goes up to plus 40 millivolt. So what we are seeing that firstly ligand gated sodium channels are open, then voltage gated sodium channels are open, sodiums are accumulating in the myocyte or the muscle fiber, depolarization occur, firstly motor end plate potential is generation, then threshold value is crossed, then more and more sodium is entering into the muscle fiber, and it goes up to the plus 40 millivolt, which is the very important step, which is the very important potential for the stimulation of opening of the voltage gated calcium channels. So in this myocyte section, there are two type of calcium channels. First one is, this one is dihydropyridine receptor, or DHPR, dihydropyridine receptor. These are the voltage gated calcium channels. And there is another type of calcium channel, that is mechanical gated calcium channels, or the ryanodine receptor. There is ryanodine receptor, or the mechanical gated calcium channels. By influencing from the voltage gated sodium channels and mechanical gated sodium channels, both are in the proximity. Hence, by the influencing of the voltage gated calcium channels or the dihydropyridine receptors, ryanodine receptor channels are also open. The ryanodine receptor also open their channels, and in the sarcoplasmic reticulum it is happening. cytoplasmic reticulum is the main source of calcium here. Okay, so there are more and more amount of calcium inside the sarcoplasmic reticulum. Right, and the due to plus 40 millivolt, due to reaching in the plus 40 millivolt, DHPR receptors or the voltage gated calcium channels are activated. They opens, and due to which rhinodine receptor channels are also opening, and the calcium and the calcium which is inside the sarcoplasmic reticulum is opening, and the calcium are moving out of the sarcoplasmic reticulum through rhinodine receptor or the mechanically gated calcium channel. So these calcium is moving outside of the cell, outside of the sarcoplasmic reticulum, and binds to the troponin. So firstly we write that it leads to opening of voltage gated calcium channels. Then what happened? This point is very important. By influencing from voltage gated calcium channel or the DHPR receptor, rhinodine receptor or mechanically gated calcium channels are also opening. Right, now calcium comes out from sarcoplasmic reticulum through rhinodine receptor. Okay, next what happened, it is mainly the molecule in the molecular level. So then the calcium binds to troponin C, which further activates the troponin T. Troponin C, troponin T, tropomyosin, these all are the part of the thin filament. So it's happening in the sarcomere itself. It is happening in the molecular level, right? So movement of tropomyosin. Next is movement of tropomyosin from the myosin binding site of actin. Basically, it's try to unmasking the site of myosin, right? Unmasking the site of myosin binding site over actin. So firstly, movement of tropomyosin from myosin binding site of actin, it is the unmasking procedure. Unmasking of myosin binding site in actin. Now it is open to actin for binding or the integration with myosin. So next, actin myosin integration will form, and then by ATP and various molecular process, muscle contraction is happening. Okay, so it is the main mechanism for excitation contraction coupling from the entry of the sodium till the voltage gated calcium channel. It is the part of the excitation. So it's basically parts of excitation. And from the from the calcium binding to the troponin C and activation troponin P till the muscle contraction. It is the contraction procedure of the skeletal muscle. So that is the contraction. So both are coupled with each other to contract a skeletal muscle. So it is the excitation and contraction coupling. Right. Now we are moving in the molecular basis of the muscle contraction. Now we are going to understand the molecular basis of the muscle contraction. Okay, let's go. So in first step, they are at relaxed state. At relaxed state, resting fibers cross bridge is not attached to actin. So there is no interaction between actin and myosin. Here is the myosin head, and these are the thin filament or the actin. There is no attachment of the actin with myosin. Right. So there is a ATP molecule which breaks into ADP plus inorganic phosphate. Next, in this breakage, some energy is produced. So this energy that is residing in inorganic phosphate. So inorganic phosphate is released from the myosin head, causing a conformational change in myosin. That myosin head is attached to the actin, to the myosin binding site of the actin. Hence the cross bridge formation occurred. Right. Then from that ADP molecule also removed. Firstly, we have to understand that that ATP is breaking down in ADP plus inorganic phosphate due to ATPase activity in myosin head. Right. So ATPase activity due to in myosin head, ATP is breaking into ADP plus inorganic phosphate and some energy is produced. Then cross bridge binds to actin. Cross bridge means the myosin head which binds to actin, binds to myosin binding site of the actin, and inorganic phosphate is released from the myosin head, causing conformational change in myosin. Then the power stroke causes filament to slide. When the ADP is released, power stroke is generated and causes filament to slide. So here sliding is occur in this direction, right? And then new ATP binds to myosin head following release from actin. So when the ATP is binding to the myosin head, then it detaches from the myosin head is detaches from the actin or the thin filament. Then the cycles goes up and ATP again hydrolyzed in ADP and inorganic phosphate, causing cross bridge return to its original orientation. So it is the main molecular basis of the muscle contraction. It is also known as sliding filament theory. So it is also known as sliding filament theory. So it is the molecular basis of the muscle contraction. Now let's see the changes in muscle contraction. We discussed over here that some lengths, some zones and bands of the sarcomere. So here we see some zones, that H zone, then some band, A band, I band, M line, Z line, which we are going to discuss what changes in these bands and zones or lines we are going to discuss in this segment. So firstly, A band. A band is the effective length of the myosin filament. So A band after muscle contraction remains same. So A bands remains same. I band is the distance from the end of the myosin filament to the Z line or Z disc. So after muscle contraction, we will see that this is I band, and the I band length is decreasing, and this is the I band after muscle contraction. So that I band shortens and tends to disappear. Tends to disappear. Right. Then H zone. Which one is the H zone? From in between two ends of the thin filament. It is the H zone. After muscle contraction, two thin filament approaches to each other, and the age zone also shortens. This is the age zone after muscle contraction, so it shortens and tends to disappear. Next, the length of the sarcomere. Length of the sarcomere, which is the length of the sarcomere between two Z disc or Z line. It is the length of the sarcomere. As muscle contracts, two Z line or Z disc approaches to each other, hence the length of the sarcomere also decreases or shortens. Right? So these are the main concepts regarding muscle contraction. Here we read about hierarchical structure of muscle, skeletal muscle, and the structures of sarcomere. Then we will thoroughly read about excitation contraction coupling. It is the very important question and a very important short note in exam also, and a very important concept also. So, and then we comes into the molecular basis of the muscle contraction and sliding filament theory. It is also an important question in your examination, and changes in muscle contraction. Next, move to the next topic or the subtopic. It is the properties of the skeletal muscle. Properties of the skeletal muscle. We will see. We will be discussing over this table between two types of muscle fibers. That's are type 1 muscle fibers and the type 2 muscle fibers. We will discuss the differences of type 1 and type 2 muscle fibers, by which we can also read the properties of the skeletal muscle and the properties of that muscle fibers. So there are two types of muscle fibers: type 1 muscle fibers and type 2 muscle fibers. Okay, so we are going to see properties of these fibers one by one. Firstly, type 1 muscle fiber. These are the small fibers. Let's write down. These are the small fibers, where type 2 muscle fibers are the large fibers. Next, these muscle fibers, type 1 muscle fibers, are innervated by small neurons. Like a beta neuron, where type 2 muscle fibers are innervated by large neurons like a alpha neurons, innervated by large neurons, a alpha neuron. Next, this type 1 muscle fibers are the slow twitch muscle fiber. And this type 2 are the fast twitch muscle fibers. How we call that slow twitch and fast twitch? We basically rely upon the concept of length tension or the force or the force time relationship, not the length tension. That is the force of contraction versus time relationship we are going to discuss. So here is the force of contraction in the y-axis and the time in the x-axis. So slow twitch muscle fibers, where the contraction started and it goes like this. It goes like this, and it is over a long time period. The force of contraction remains over a long time period. Where in case of type 2 muscle fibers, again force of contraction and time. So it is as it is the first twitch, so it is the starting point of the contraction, and it goes like this, and it is the short time period. So type 1 muscle fibers are the slow twitch, whereas type 2 muscle fibers are fast twitch muscle fibers. Next is rate of myosin ATPase activity. In the type 1 it is slow, and in the type 2 it is very fast due to fast twitch, and in type 1 it is slow twitch, so the rate of the myosin ATPase activity is slow here. Rate of myosin ATPase activity is slow here, whereas rate of myosin ATPase activity is fast in case of type 2 muscle fibers. Number 5. Now we will discuss some cell organelles in this difference. So firstly, mitochondria. Mitochondria is high in number, whereas in type 2 muscle fiber, mitochondria is low in number. Next, sarcoplasmic reticulum. It is very low in number, and in the type 2 muscle fibers, sarcoplasmic reticulum are very high in number. As there is high density of mitochondria, so the oxidative capacity of the type 1 muscle fiber are very high. It is very high. Oxidative capacity is also higher. But in type 2 muscle fibers, as there is low mitochondria, oxidative capacity also low here. Next one, fatigability. Fatigability is the long duration how much it gets fatigue. So fatigability is less in type 1 muscle fibers. Also they are slow twitch, right? So they are less fatigue, whereas in type 2 the type 2 muscle fibers are more fatigue, so fatigability is more here. Myoglobin content, as the oxidative capacity is high here, you must have understand that oxygen demand is very high in this type of muscle fibers, that is the type 1 muscle fibers. Oxidative capacity is high here, so the myoglobin content in this muscle fiber is high, so the myoglobin content is very high. Actually this point should above the oxidative capacity, but it's okay. So in contrast, in type 2 muscle fibers, myoglobin content is low. Right. Next uses. Next, capillary density. Capillary density also high in type 1 muscle fibers, and in type 2 muscle fibers capillary density is very low. Next, capillary density. high and capillary density is low here. Uses more sustained activity or endurance for more sustained activity for a longer period of time. Type 1 muscle fibers are required. More sustained activity or more endurance, whereas type 2 muscle fibers are required in very brief muscular activity. Uses brief muscular activity. So type 1 muscle fibers examples are soleus, in standing like 1 hour or 1.5 hours in a train. So here we use soleus as soleus. So soleus is a type 1 muscle fibers, but in like lateral rectors or the gastrocnemius, these muscles are the type 2 muscle fibers. So their work is very brief, but in case of type 1 muscle fibers, their work is for a sustained period of time. So examples are not the differential points here. So examples of the type 1 is soleus, and in this case in the type 2 muscle fibers, examples are gastrocnemius and lateral rectus. Okay, next last but not the least, length tension relationship. In length tension relationship, 3 points are very important. Here you study the preliminary or the basics of the length tension relationship. In cardiophysiology or in the heart section of the physiology, you are going to study that Frank-Starling law. So it is a bigger concept. So it is a preliminary concept which is length tension relationship. Length of a sarcomere at which maximum tension is generated, that is known as optimum length, right? So first point is length of sarcomere at which maximum tension is generated. So that length of the sarcomere is known as optimum length. Okay, next point number 2. Every skeletal muscle will contract at maximum length, at maximum tension. So beyond that tension it cannot contract further. So every skeletal muscle will contract at maximum tension. And the last point is any length beyond or under the optimum length of the muscle, their force of contraction required less, or the tension is less there. Okay, any length less than or greater than or the under or the beyond of optimal length leads to reduced force of contraction or less tension is required. Okay, so the curve looks like this. The length increases, the tension increases at a optimum length. At optimum length, tension is high. This is the highest tension. Then again, however, the length increases, but the tension is going to decrease, right? So this is the length tension relationship. So here it is the optimal or resting length of the sarcomere. So in this portion of the properties of the skeletal muscle, we discuss about different muscle fibers like type 1 and type 2 muscle fibers, their properties, and a very important but little bit of concept, that is the length tension relationship. So these are the important topics over here. Now I will point out some important questions of the topics for the exam, university exam point of view. So from here, the mainly important topics are the action potential and the neuromuscular junction and the mechanism of the muscle contraction. These are the main important topics for the exam point of view. So firstly, phases of action potential. It is a must known topic for exam, right? Then refractory period, it will come as a short note, okay? Then in neuromuscular junction, mechanism of neuromuscular transmission, it is also an important question for university exam. So you have to write this kind of flowchart, and if you put a diagram like this, you will get the full marks, okay? Then pathophysiology of the neuromuscular junction, it is very important topic for any kind of exam, for any kind of university exam, because it is also repeat in pathology. Yes, and it is also a question in physiology. In physiology point of view, you have to know the pathophysiology of the myasthenia gravis. Mainly the question is coming from myasthenia gravis also. Myasthenia gravis and the difference from myasthenia gravis, depends between myasthenia gravis and the Lambert-Eaton syndrome, and the treatment of the myasthenia gravis. This comes as a broad question or the 10-mark question, right? So this is important. Pathophysiology of myasthenia gravis is important. Difference between myasthenia gravis and Lambert-Eaton syndrome, it is also important. And the treatment of myasthenia gravis, both the treatment, neostigmine and the hydrophonium challenge test, both are important, and hydrophonium challenge test will come as a short note. Then in mechanism of muscle contraction, most important thing is the structure of sarcomere. It is the most important here, and the excitation contraction coupling, it is also come as a short note. So and obviously, and the molecular basis of the muscle contraction will also come as a short note. So that is all for nerve muscle physiology point of view, and that's all, guys. Thank you.